You've probably heard that neural networks work like the human brain. But here's the thing. They don't, not even close. Your brain has 86 billion neurons making a quadrillion connections, running on the same power as a light bulb, somehow creating consciousness. A neural network, it's basically just really fancy pattern-matching math. And yet this fancy math can look at a photo and tell you it contains a golden retriever wearing sunglasses. It translates languages in real time. It beats world champions at games we thought required human intuition. So what's actually happening inside these things? And why does everyone keep calling them intelligent when they're really just calculating? Let me start with what a neural network actually is, because the brain comparison has confused everyone for decades. Imagine you're deciding whether to go outside based on the weather. You look at three things: temperature, cloud cover, and wind speed. But you don't just add these up, that'd be weird. Instead, you weigh them differently. Maybe temperature matters most to you, so you give it more importance. Cloud cover matters some. Wind speed, barely at all. So you might think, temperature gets 70% of my attention, clouds get 25%, wind gets 5%. Then you combine these weighted factors and decide, yes, I'll go outside, or no, I'll stay in. That's essentially what one artificial neuron does. It takes inputs, multiplies each by a weight that shows how much it matters, adds them up, and makes a decision: output something or don't. But here's where it gets interesting. You connect hundreds or thousands of these simple decision makers together in layers. The first layer looks at raw data: pixels in an image, words in a sentence, numbers in a spreadsheet. Each neuron makes its own simple decision based on what it sees. Then those decisions become inputs for the next layer of neurons, and those neurons make slightly more complex decisions based on the simple ones from before. Layer by layer, the decisions get more sophisticated. It's like an assembly line of judgment calls. The first worker might just sort things by color, the second worker groups the red things by shape. The third worker decides which red round things are actually apples. By the end, you've gone from raw pixels to "this is a Granny Smith apple," 87% confidence. The neural part isn't because it works like your brain, it's because each artificial neuron makes a simple decision and passes it on, sort of like how your neurons fire or don't fire. But that's where the similarity ends. Now let's see exactly how this assembly line works, because the magic is in the details. Picture a neural network like a multi-story office building. The ground floor is where raw data enters. Maybe it's the pixels of a photo you want the network to identify. Let's say you're trying to identify handwritten numbers, and you feed in a 28 pixel image of someone's handwriting. That's 784 pixels, so you have 784 input neurons, each holding 1 pixel's brightness value. The second floor is your first hidden layer. Let's say it has 128 neurons. Each of these 128 neurons connects to all 784 input neurons below. That's over 100,000 connections just between the first two floors. Here's the crucial part. Every connection has a weight. Think of weight as how much should I trust this input. Some connections have high positive weights. If this pixel is dark, that's important evidence. Others have negative weights. If this pixel is dark, that's evidence against my theory. Most start random and get adjusted during training. So neuron number 47 on the second floor takes all 784 pixel values, multiplies each by its specific weight for that connection, and adds them all up. Let's say it gets 2.7 as its total, but here's where the activation function comes in, and this is what makes neural networks powerful instead of just fancy calculators. The neuron doesn't just pass along 2.7. Instead, it runs that number through a function, let's say ReLU, which is simple. If the number is positive, keep it. If it's negative, make it 0. So 2.7 stays 2.7, but 1.3 becomes 0. Why does this matter? Without activation functions, no matter how many layers you stack, you just have a very complicated linear equation. The activation function introduces nonlinearity. It lets the network learn curved relationships, complex patterns, weird exceptions to rules. This process repeats floor by floor. The 128 neurons on floor 2 each make their decisions and pass them to floor 3. Maybe floor 3 has 64 neurons, each connected to all 128 neurons below it. Again, every connection has its own weight, learned through training. By the time you reach the top floor, the output layer, you might have just 10 neurons, one for each digit, row through 9. The neuron that fires strongest is the network's best guess. But here's what's wild. Nobody programs what each neuron should look for. Through training, they automatically specialize. Some neurons in early layers might become edge detectors. Others might detect curves. Deeper layers might detect more complex features, like the loop in an 8 or the crossing lines in a 4. The network discovers these patterns on its own by seeing millions of examples and gradually adjusting its weights to minimize mistakes. Now here's where it gets messy, because everything I just described is the clean, simple version. Real neural networks are wonderfully, frustratingly complicated. First, let's talk about training, because that's where the real magic happens, and where everything can go wrong. Training a neural network is like teaching someone to recognize faces by showing them millions of photos and telling them when they're wrong. Except instead of one person, you have thousands of artificial neurons, each making slightly different mistakes, and you need to figure out exactly how much each neuron contributed to the overall error. This happens through backpropagation, literally backward propagation of errors. When the network makes a wrong guess, the error signal travels backward through all the layers, and each connection's weight gets adjusted slightly. The connections that contributed most to the error get punished more, the ones that helped get rewarded. But here's the first complication. This only works if you have the right answers to train on. That's supervised learning. You show the network millions of labeled examples. Want to recognize cats? You need millions of photos labeled cat or not cat. Want to translate languages? You need millions of sentence pairs in both languages. What if you don't have labels? That's where unsupervised learning comes in, and it's much trickier. The network has to find patterns without being told what to look for. It's like asking someone to organize a library without telling them what the books are about. Then there's the architecture problem. How many layers should you have? How many neurons per layer? This isn't just academic. It changes everything. Too few layers, and your network can't learn complex patterns. Too many layers, and you get the vanishing gradient problem. Here's what happens. Remember that error signal traveling backward? In very deep networks, by the time it reaches the early layers, it's become so weak that those neurons barely learn anything. It's like trying to hear a whisper after it's traveled through a 100-room mansion. This problem stumped researchers for decades until they invented clever solutions like skip connections and different activation functions. Deep learning, networks with many hidden layers, only became practical in the last 15 years because of these breakthroughs. But wait, there's more complexity. Different types of neural networks work completely differently. The basic feed-forward network I described is just one type. Convolutional neural networks used for image recognition don't connect every neuron to every other neuron. Instead, they use filters that slide across images, looking for features like edges and textures. It's more like having specialized detectives who only examine small neighborhoods of the image at a time. Recurrent neural networks have memory. They can remember what they saw earlier when processing sequences. They're essential for language tasks because the meaning of a word depends on the words that came before it. And then there are transformer networks, which revolutionized AI by figuring out how to pay attention to the most relevant parts of their input. When translating "the bank of the river was muddy," they learned to focus on river to understand that bank means shoreline, not financial institution. Each architecture solves different problems, and choosing the wrong one is like trying to cut paper with a hammer. Technically possible, but you're making life way harder than it needs to be. So why should you care about any of this? Because neural networks aren't just academic curiosities anymore. They're quietly reshaping your daily life in ways you might not realize. Every time you unlock your phone with your face, a neural network analyzes your features in real time. When Netflix suggests what to watch next, neural networks predict your preferences based on viewing patterns from millions of users. That spam filter protecting your inbox? Neural network. The voice assistant that understands your mumbled questions? Neural network. The GPS that routes you around traffic? Neural networks processing real-time traffic data. But here's what's more important. Understanding how these systems work helps you understand their limitations, and that matters for your decisions. Neural networks are pattern-matching machines, not reasoning machines. They can identify a stop sign with superhuman accuracy, but they don't understand what stopping means. They can write poetry that sounds beautiful, but they don't understand beauty. They can diagnose diseases from medical images, but they don't understand health. This distinction matters when you're deciding how much to trust AI systems. A neural network that's 99% accurate at detecting tumors in medical scans sounds amazing, until you realize that 1% error rate might mean missing one cancer case out of every 100. Understanding the technology helps you ask the right questions. What was it trained on? What are its failure modes? When should you get a second opinion? There's also the economic reality. Neural networks are transforming entire industries, and that affects your career prospects whether you work in tech or not. Radiologists need to understand how AI will change medical imaging. Lawyers need to know how AI will affect document review. Teachers need to think about how AI will change education. But perhaps most importantly, neural networks are teaching us something profound about intelligence itself. For decades, we thought intelligence required consciousness, reasoning, understanding. Neural networks suggest that maybe intelligence is more about pattern recognition than we realized. They're not conscious, but they can translate languages. They don't understand meaning, but they can write coherent stories. They don't have emotions, but they can compose music that moves us. This challenges fundamental assumptions about what makes humans special. That doesn't mean we should fear AI or worship it. It means we should understand it well enough to shape how it develops and how we integrate it into society. Here's what neural networks actually are. They're sophisticated pattern-matching systems that learn by adjusting millions of weighted connections between simple processing units. They're not brains, they're not conscious, and they're not magic. They're just really good at finding patterns in data. The intelligence emerges from layers of simple decisions, building into complex behaviors, like how a flock of starlings creates beautiful, coordinated flight patterns, even though each bird is just following simple rules about its neighbors. Neural networks have transformed AI because they can automatically discover the features that matter for a given task, rather than requiring humans to hand-code every rule. But they're still fundamentally limited by their training data and their architecture. Understanding this helps you navigate a world where AI is everywhere, but intelligence is still rare. Neural networks are powerful tools, not digital minds, and knowing the difference helps you use them wisely and know when to think for yourself.